embedded into the production rule. Now, it is very important to understand the relative ordering of these actions. Like, for example, this is print star, print plus. If you change this to here, then the whole thing changes, as we'll see later. Okay. So this will be printed. What is the difference? The difference is that here, this program fragment will be uh, called in action after you have evaluated E and before you have evaluated T. Whereas in the other case, this action will be invoked after both E and T are completely taken care of. Means you have created a parse tree where both E and T have grown into a fully developed branch. There is nothing else pending, and then only this programming action will be taking place. So where you are putting the action is very important, and that is what we are going to actually play with in today's course, in today's class. So
Sir, in conversion of infix to postfix, we use SDT also.
Pardon? SD?
Sir, SDT is used for conversion of infix to postfix. Can we use SDT there?
Yeah, that is what we are coming right now. But not only for this thing, you can do it for, in fact, you have to do this for all kind of programming actions. Like whenever your parser is done, parser means what? Parser means you are basically writing the context-free grammar in an appropriate manner, right? That's what the parser means. And then you are producing the parser table. So in general, if you have a Bison-like thing, you don't really do anything with the parser because you just input the context-free grammar and it creates the parser automatically for you, right? But you need to embed the actions, and that is what the syntax directed translation scheme is. Now, whatever you have done in Bison classes, these were all basically syntax directed translation, nothing else. So I told you that we were actually doing parser or parser generation, but in effect, we were actually writing the corresponding syntax directed translation scheme for each of the production rule in the context free grammar. Okay. So here you can see infix to postfix translation. So the SDD and SDT for this particular grammar. So E producing E plus T. So you have infix expression. So where the operator is in the middle, and so you have to produce a postfix ones where the operator is at the end. So you can see the action. What it does is it first fully evaluates the expression E plus T and then prints the operator at the end. That's what was intended. Okay. And whenever it gets a 0 or 1, it prints the operator first. The operand first. And then that means if you have an expression like this, I'm showing you an expression which you can use for explaining this. Let me see if I have an example here itself. No, it's not there. So let me do it. Okay. Now just understand the difference between SDT and SDT is that in SDD, you don't embed the programming fragment. There is no print statement or anything like that, which is programming construct, but you just create the attributes. You just populate the attributes like e.code or t.code. So suppose I do something like this. Very simple one, 9 minus 5. So this is 9 minus 5. Okay. So if we parse it, what is the grammar? Let us go back to the grammar again. just look at the SDT part, not SDD part. So it is going to be like this, something like this. E producing E minus T, then E producing T, and T producing 9, and this T producing 5. So this is the corresponding parts tree. So once this parts tree is constructed, as you can see, print plus is at the end of this production rule E producing E minus T. So what it will do is, so first I'm coming here, so T producing 9. So what is going to be printed? So this is the output. So output will be printed as 9. Okay. Then you go to T, because after minus you are not doing anything, and then you go to T, and then you are producing 5. So that means after 9, 5 will be produced. And then you complete the action, you complete this action, and after that the minus printing action is invoked. So to get this. So that means you get the postfix expression corresponding to 9 minus 5. Okay, this is the spirit. Now, if you misplace that program fragment somewhere else, then it would have been disaster. Okay, so you can easily understand that if I want, okay, can you tell me this thing? If I want to convert this infix grammar into a expression into a prefix expression, how should this SDT scheme look like? Can anybody tell me what needs to be changed? Yes. So what should I do with this rule? This is the rule that needs to be changed. E producing E minus T, and we have print minus here. So somewhere some changes need to be made in this SDT scheme. What should be done? Yes? Any idea? What should I do? Yes? Anybody? So I want to convert this infix expression 9 minus 5 into a prefix expression instead of a postfix. So what should I do? That means operators will be before the operands. Can you tell me what needs to be done? Yes? Any idea? Okay, I leave it as an exercise. I'm not going to say this. Anyway, I think you are not seeing it. I'm sorry. I need to share my screen. Okay, sorry. Let me share it. Okay, can you see this now? That E producing E minus T, the action took place. So from 9 minus 5, it produced 9, 5 minus. This is what is produced. Now, what I'm saying is, from 9 minus 5, I want to get this. Minus 9, 5. So I tell you that this rule needs to be changed. The semantic action, sorry, not the rule, but the syntax, the SDT action of this rule needs to be changed. So can you tell me what should I do? I have got this, no problem. This is fine. But what about this? How do I get this from here? This needs to be changed. Only this thing needs to be changed. What should I do? Anyway, I leave it for an action, for your action. Okay. So let me check the next one. So SDD is a CFG along with attributes and rules. An attribute is associated with grammar symbols. So all the symbols have some attributes, not necessarily, but the ones we are interested in should be having attributes. And rules are associated with productions. So this is where the concept of rules, productions, attributes, grammatical symbols, uh, these are important. Now, please, this is an important slide, so please look at it carefully. Attribute is any quantity associated with a programming construct. So what kind of uh, attribute can programming constructs have? Like, for example, the data type, line number, instruction details. These are all programming constructs which have corresponding attribute. Like, for example, you can say code is an attribute of a programming particular line in a program. Okay, which is basically the verbatim code of that particular programming program line. Or you are using a variable, so the data type can be an attribute of that variable. Also, you can use the line number where a particular programming construct is used. Okay, either a control statement or some kind of a data assignment statement. So all these things are essentially attributes of any programming construct. There are two types of attributes or two kinds of attributes which are very important for our understanding of SDT or SDD. Please carefully note them. One is known as synthesized attribute, another is the inherited attribute. So can you tell me, if I tell you that I have a non-terminal A and its attribute is ABC, and it is a synthesized attribute, what is the first thing which come to your mind? What do you mean by synthesize? And what do you mean by inherited? Suppose I say DEF is a so there are two grammatical rules, and so there is a grammatical symbol A and it has an attribute ABC and another attribute DEF. This is an inherited attribute. So what do you mean by inherited attribute? Can anybody try to explain me from the concept of parse tree? Intuitively. So suppose you are creating a parse tree like this. Suppose B producing A and say X, something like that. So that means A has an attribute DEF, which is coming from this guy. Inherit means you are inheriting from the parent. That's what it is. Inheritance is always from the parent. So an inherited attribute is basically a semantic rule associated with the parent production of that particular node N. So you have a tree node N and it has a parent. So an attribute which comes from the parent is basically an inherited attribute. Now, please note that it is not only parent, but it could be siblings of N as well. Okay. In case of a synthesized attribute, which is again defined here, it is basically coming from the children. So there are two types of attributes you can have. So A can get it from its parent, A can get it from its sibling, or it can further produce C and D. So it can get the attribute from its children as well. So these are the only ways A can get its attribute. Or of course, it can carry its own attribute as well. Okay. So these are the only possible ways of populating an attribute for a particular non-terminal A, which is shown in this particular diagram. So it can either get it from the parent or from its siblings. In that case, that attribute is an inherited attribute. If it gets it from its children, then it is a synthesized attribute. Okay. All right. And if it is own attribute, it can either be inherited or synthesized. It can be both, basically. So we don't really distinguish that. So our main concern is whether it is getting the attribute populated from its parent and sibling, or it is getting the value populated from its children. This distinction is very, very important when we go about exploring the syntax directed translation scheme or the semantic actions. Alternatively, this is known as the semantic action as well, instead of syntactic action, which is handled by the parsers. Yes, Pranay?
Real attribute, sir.
Pardon?
Sir, this synthetic and inheritance are real attribute.
I cannot hear you. You are breaking.
Sir, the synthetic, synthesized and inherited attribute, can I say it is real attribute?
No, I'll come to that. A lot of people make this mistake. Okay. And this is a very popular question with me because people generally think that inherited attributes are L attributed and synthesized attributed are S attributed. We'll come to that. This is not correct. Okay. Okay. So this is a grammar where we have added the attributes. You can see L has attribute dot in, T has attribute type dot type, um, and that's about it. So L dot in equal to T dot type. So this is how populating the values are done. So can anybody tell me for the first production rule, D producing TL, what kind of attribute is L dot in? Is it synthesized or is it inherited?
Sir, pardon, please may you repeat once again?
Yeah, I'm talking about the first rule, D producing TL. Okay, let me write it down on that screen. Okay, suppose I have this kind of a rule, D producing TL, and I say the corresponding action is L dot in is assigned the value T dot type, assuming T dot type is already populated. So from T dot type, L gets its attribute L dot in. So can you tell me what kind of attribute is L dot in?
Sir, L dot in, L dot in is synthesized attribute, sir.
No, L dot in is not synthesized attribute because, as I said, L dot in is getting the attribute value from whom?
T.
From whom? From T.
From T or D, sir.
No, not D. It is getting it from T as it is written. L
Yes,
dot
sir,
in
T.
is assigned the value T dot type. So T dot type, so it's getting the value from T. And what is the relationship between L and T? What is T with respect to L? Is it
Sir,
parent?
T is a parent of L. No, T is a sibling of L.
Right. T is a sibling of L. And as I said, if it gets a value from its sibling, attribute value from its sibling, then it is an inherited attribute. Okay.
Sir, but it should be in the left side. No, the sibling, I can take value from sibling who is in my left side, I think.
No, that definition is not there in inherited attribute. That is there in L attribute. I'll come to that. That's why I said L attribute and inherited attributes are not the same. Okay. So there is nothing mentioned in inherited attributes that it has to be from left sibling. But what you are saying is correct. For L attributed grammars, that's what is going to be true. Anyway, all right. So T producing int and T dot type is integer. It's basically neither parent nor sibling nor child, nor children. It is itself. The attribute is uh, populated by itself. But you can see L producing L1, comma ID. L1 dot in is L dot in. So can you tell me what is this kind of attribute L dot in? Again, it is inherited because here it is inheriting from the parent. Okay. So interesting. We'll see a mixture of these things as we go forward. Now, this is an interesting one. We'll be using this to show an example. Unfortunately, I don't have too much time, so can't use too much of time, but I'll try to explain as much as possible. So this is a production rule, set of production rules, as you can see, num producing sign and then list. Sign can be plus or minus. List can be bit or list followed by bit, and bit can be 0 or 1. Okay. The attributes are dot pos, dot neg, dot val, and that's it. Okay. So it's basically trying to evaluate from given binary um, expression, binary number, what is the equivalent decimal number. That's what it is trying to figure out. So let us try with a number, say minus 109, 101, minus 101. So what is the corresponding value? Okay. So we start with num and then we grow, and it's basically S and L. Okay. So you can see in this particular action, okay, I'm sorry, the action is not shown. Only the rules are shown, but okay, I haven't really, I don't really care about that. Okay, yeah. So N is producing S and L, and S is producing minus, and L is producing L and B, right? There are 3 bits. So this is again going further down, and it's producing again L and B.
Sir, this L and B is
Is
just name or
list
L is
list and bit.
okay, sir.
Okay, and then we have L and B. Is that true? No, I'm wrong. B is producing a B. This is the rule which is used. Okay, and here this is nothing but 1. This is 0, and this is 1. Okay, so now what are the attribute values as each node? Now bit can have value either 0 or 2 to the power bit dot pos. So bit has an attribute dot pos, dot position. So dot position it will get from, as you can see, it will get from this particular rule says bit dot position is available from list dot position. So whenever list dot position is available, bit dot position will be available. So list dot position is initialized to 0 here, which is this rule right here. So here the pos value is 0. And then this creates L and B. And here you can see the position value is incremented. So here the position value is 1. And hence, since B gets the position value from L, the position value will be 1 here. Here, the position value is 2. Hence, this position value Yeah, this is also 2. Actually, there is a little bit of a mistake here. Anyway, here it is also 2 because from L producing B, the position value is inherited from L. So this is also 2. Okay. Now, what is the other set of attribute? The other set of attribute is val. So what is B dot val here? Right here. Let's calculate. So this value is 2 to the power 1. So which is 2, and here the value is 0 anyway, because when the digit is 0, the value is 0, and here the value is 2 to the power square, which is 4. Okay. Now, what is the value here? Dot value here. It is the value of L and value of B. Value of L is 4. Value of B is 0. So it is equal to 4. What is the value here? Left side has 4, right side has 2. So it is the value 6. And this is the value.
Sir, may you repeat this?
Yes. Okay. So you can see there are two sets of attributes, pause and val. So pause is an inherited attribute. So first, this node right here is getting the value of pause as 0 from this rule.
Yes, sir.
Okay. Then L produces L and B. Each time L produces L and B, L increments his pause value by 1, as you can see from the rule.
Yes, sir.
Okay.
Yes, sir.
And that position value is assigned to
B.
Okay. Yeah, I'm a little wrong here. This should be 0 because it is coming from L, not this L, from this L. As you can see, bit dot position is list dot position, not list one dot position. Okay. So this is 0, and
Sir, and this position will be 1, I think.
this will be 1, right? This will be 1. Okay. So this will be 1.
And final B will be 2, I think.
Final B will be 2. Okay. So this becomes 2 square, and this value is actually 1, not 2. So val is what? Val is, if bit is 0, val is 0. Of course, this value is 0. As you can see here, this is just 0. This value is 2 to the power naught, which is 1. And this value is 2 to the power square, because if bit is 1, bit dot value is 2 to the power bit dot pause. The bit dot pause here is 2. So value is 4. 4 is nothing but 2 square. So this value right here comes, and then this comes as 1, and the value here is computed as 4 plus 1. You can see the calculation right here. L producing LB, it's basically L dot val equal to L1 dot val plus B dot val. So L1 dot val here is 4, B dot val is 1. So this becomes 5. Now let us come to N and S. N and S, as you can see, if sign dot neg is true, then num dot value becomes negative. If sign dot neg is not true, then it becomes a positive. So what is sign dot neg here? As you can see, if it is a minus, then this dot neg is equal to true. So right here, n checks sign dot neg is true. So the value given by L, which is 5, will have a negative here. So n dot val will be -5.
স্যার এই মাইনাসের গল্পটা একটু ক্লিয়ার হলো না স্যার।
এই দেখো,
হ্যাঁ,
n producing SL. S is the sign.
yes sir.
S is a negative here. So the moment you have a negative here, the attribute dot neg is set to true.
Yes sir.
When n tries to evaluate the value here, it checks this sign dot neg. Since sign dot neg is true, it will have a negative value. If sign dot neg is false, it will have a positive value. Okay, that's what it is. Okay, this is an example how values are inherited or synthesized from different nodes. Now you can ask this question, sir, how were these values populated? Were you doing a top-down translation or a bottom-up translation? I haven't assumed anything here. I just showed that somehow the values got populated, and once the populated values were there, then depending on whether it is inherited or synthesized, it got populated appropriately, either from children or from parent or sibling, and then the final value was returned. Now, you can readily understand if it is a synthesized attribute, that means you get the values from children, then which one is easy, bottom up or top down? Which one will be an easy thing to do? Shall I do a bottom up translation or shall I do a top down translation when I have synthesized attributes only? Who can tell me?
Sir, top down
Why?
for the synthesis.
Yeah.
Uh,
Not synthesis, synthesized.
Synthesized. Just I guessed it.
No, just try to think this way, that you need to know the value of a when you are trying to evaluate the attribute of a particular node. In case of synthesized attributes, you need to know the value of the children first, right? Right?
Yes, sir. Yes, sir. Yes, sir.
So if you have the value of the children first and then you
Bottom up. That will be
yes,
better.
absolutely. So if you have a bottom up parser and if your grammar consists only of synthesized attributes, then there is no problem. It is the simplest of the cases. In all the other cases, we will run into lots of problems and we will be fixing it, and part of it will be fixed during the
Hello.
Okay, so we agree that if your grammar essentially only has semantic actions that consist of synthesized attributes, and if you are using a bottom-up parser, it is the simplest of the cases, because when you are using a bottom-up parser, for a particular node, all its children are evaluated first before that node is evaluated. So you can easily synthesize values from its children, because the values of the attribute values of children are known before the particular node is created. That's the simple answer. Okay, now for any of the other cases, like when you have a bottom-up parser and you have inherited attribute, what will happen? When you have a top-down parser and you have synthesized attribute, what will happen? When you have top-down parser and you have only inherited attribute, then also you'll see some issues will be there, because it might be natural to think that if you have a top-down parser and you have only inherited attributes, then it is easy because you know the values of attributes of parent before you start evaluating the children. You are not wrong, but then the complexity comes with children. Okay, sorry, siblings, because you may be siblings, you may be having siblings which are right of you. So what will happen? Because as we know, in top-down parser, it is always a left to right scanning. So first the left branch will be done and then only right branch will be done. So if the attribute of a particular node depends on right siblings, what will happen? To simplify such cases, we have some simplifying assumptions. As Pranay was trying to point out, sir, it should depend on left sibling. We'll see that it is indeed the case. Okay. And the worst thing is, most of the time, you will have, like the case we are trying to explain, in case of -101, you have seen that it is a mixture of inherited and synthesized attributes. So what should be the strategy? Okay. So it seems that neither um, bottom up nor top down is sufficient to handle such cases. We'll try to explain some of these as we go forward.
Sir, can we follow Ullman for this part?
No, it is Ahulman. Yeah, that is the one. This is the book. I don't follow any other book. Okay, this is, you can see an explanation of the parts tree and the nodes containing the attributes, just what I have explained a little bit back. Okay. This is another grammar, and we have semantic actions. So this is our old grammar, L producing E. So this is the expression grammar we have already talked about in detail in our parser activities. So E producing E plus T, E producing T, T producing T star F, T producing F, F producing parenthesis E, and F producing digit. And these are the actions. E dot val. Digit dot lexval is basically the lexim, you can say, for the digit. Like if the digit is 9, the value returned is 9. Okay, that kind of thing. So that you can do the arithmetic operations on that. So when you are evaluating T dot val equal to T1 dot val into F dot val, then T1 dot val and F dot val both are numerical values, because digit dot lex val essentially returns a numerical value corresponding to the particular digit. Okay, that's what it is supposed to do. And this is an example. As you can see, okay, by the way, this kind of parse tree where you have the attribute values explicitly mentioned is also known as annotated parse tree. Please note that. Sometimes people ask these questions, what is the annotated parse tree for this? So you not only create the parse tree, but you populate the attribute values at different nodes in the process. Okay. Like here you can see 3 star 5 plus 4 followed by n. So what is the corresponding action? Okay. Let us try here again. So we have 3 star 5 plus 4 and n. Okay. So this is basically F producing digit. So digit has the value, it is 3. So F dot value is 3 also. Similarly, this will have the value 5. This will have the value 4. Okay. Now then, this will be actually evaluated to T star and this guy. So this value is what? This is 3, this is 5, and we are doing a multiplication, so this becomes 15. And then we have the plus here and the 4 here. So the value here is 15 plus 4, 19. Can you tell me what kind of parser is suitable here and what is the type of attribute we are using here. Is it synthesized attribute or inherited attribute? Is it a bottom-up parser or top-down parser, which will be easier to use? Can anybody tell me? Yes? Dot val, is it a inherited attribute or synthesized attribute? And the parse tree, is it easy to construct in a bottom-up manner or top-down manner? Just think about it. Okay. This is another example of attribute grammar on page 12, and page 13 is an example of this. Here we are actually dealing with inherited attribute.
Sir,
Yeah.
if a single sentence there is two inherited and one synthesized, so I cannot say that is real attribute, no?
No, I'll come to that. Okay. Let us first finish these things, then we'll go to the L attributed definition and S attributed definition. I'm coming to that. Okay, this is another example. This is the parse tree for this particular grammar, and you will particularly want to see how the inherited attributes are populated here. Next is DAG or directed acyclic graph for expressions. This is very important in code optimization in particular, since optimization is present in many places in compiler. Constructing a DAG sometimes can give you interesting hint about redundancy in your programming, like common sub-expressions. So you have same expression repeated because compiler is a mechanical tool. So sometimes same expression is repeated across different part of the program. So by constructing a directed acyclic graph for such expressions, you can easily remove redundancy, for example, and there may be other things. So a directed acyclic graph for an expression identifies the common sub-expressions in the expression. That's what it is meant for. A DAG has a node for every sub-expression of the expression. Okay. So that means if you have A minus B, that will be having a node. Then if A minus B is added with C, then that will be another node. Very similar. I think you have already seen this. We'll see an example. A node in a DAG represents a common sub-expression that has more than one parent. So let's look into these. Like for example, A star B minus C. This is the expression, and we want to construct the, A plus A star B into C plus B minus C star D. This is the expression. So let us try to construct the DAG for this. This is the expression. A plus A star B minus C plus B minus C star D. So how do we construct the DAG for this particular expression? Okay. So what we'll do is, so we can see that B minus C is an expression. So we can do like this. B minus C. Okay. Now this B minus C is multiplied with A and also you can see this B minus C is multiplied with D. So you can do this. Okay, so as you can see, this B minus C is common sub-expression for two sub-expressions, A star B minus C and B minus C star D. So you can see only this node is used. So that way you can easily identify common sub-expressions. Okay, and now you add A into uh, A star B minus C. So there is a plus node, this and this. So this is A plus A star into B minus C. And then you add that with this guy as well. So this becomes your DAG for the expression which is shown on the right hand side. This kind of constructs may come in your exam, simple one. So whenever you see the internal node, try to evaluate it first. Like B minus C is a parenthesized node that should be evaluated. Then it should be multiplied. And whenever there is a common sub expression, like B minus C appears twice in this particular expression, you reuse the same part of the DAG, which I have shown in circle. Now we come to the evaluation part of this particular strategies. So if it is a bottom-up evaluation, and if we have only S attributed definitions. So what is an S attributed definition? As you can see, S attributed definitions, these are syntax directed definitions with only synthesized attributes. So please note this. S attributed implies only synthesized attributes. Be very specific about it. So if you have an S attributed syntax directed definition, that means the type of attribute supported is only synthesized. Okay, please note this. Very important. Is important. But simple.
So this part is also important for GATE, I think.
Yes, very much. Most of the questions in compiler, I mean, parser is a huge thing, so you will get some questions from parsers. But the real difficult part to understand, compiler is not a very difficult subject, but this part, syntax directed definition and ICG, these are difficult because it is a recursive thing. So where you put the action can make heaven or hell difference. Okay, so that's what you need to understand. Where to put the action. Otherwise, everything is easy in compiler. It's just you have to be tedious. Synthesized attributes can be evaluated by a bottom-up parser, as the input is being parsed, because this is the way you construct the bottom-up parse tree. So whenever your bottom-up parse tree node is created, that means all its children are created as well. So their attributes are available. So of course, the parent attribute will be easily available from the children. Okay. So the parser can keep the values of the synthesized attributes associated with the grammar symbols on its stack. So that's the only change you have to make with the stack. You have to push the attributes as well, not only the symbols. Whenever a reduction is made, the values of the new synthesized attributes are computed from the attributes appearing on the stack for the grammar symbols on the right hand side of the reducing productions. So what it means is that, suppose this is your node A, and this is now created out of B and C. So B and C were already created, then only A is created. So if A has an attribute dot A, which depends on, is a function of attributes of B, say B dot B, and capital C dot C, by the time A is being evaluated, this A is being evaluated, both B dot B and C dot C are available, and they are available on the stack top. So a reduction is made means you are basically constructing the root of a subtree, this guy. So its attribute can easily be computed from B dot B and C dot C. This is the function which represents the dependency. So that means if you are using a stack, the only thing you need to do is push the attributes as well. That's what it is. So whenever a reduction is made, the values of the new synthesized attribute, that means the attribute of the new root, are computed from the attributes appearing on the stack for the grammar symbols on the right side of the production. Where are the right side? They are inside the stack, and they are the basically children of this particular node to be created. So you can easily evaluate it. Okay. So now the remaining 2-3 slides actually deal with how the parser stack is enhanced to handle this, which I am omitting to save time. It's very easy. You can just read it. The idea I have already given. Okay, now I'll take a 10-minute break, and then I'll come back with explaining the remaining part, which is going to be basically the L attributed definitions and how we'll handle the complexity of inherited and synthesized and top down and bottom up, all those fiasco. So I'll take a 10-minute break. I'll come back on 140, sharp at 140, and then we'll complete it as much as possible. Will be off at today. Okay. Just I have come back after the small break. So we have seen S attributed definitions and why it is easy to use a bottom-up evaluation scheme. And we have also hinted at the changes that to be made on the stack configuration to handle the synthesized attributes or S attributed grammars. Okay. Now we'll go to the next part, which is basically the L attributed definition, which is the counterpart of S attributed definitions. So please look at the definition carefully. A syntax directed definition is L attributed if each inherited attribute of xi or xj, when j varies from 1 to n, for the production A producing x1, x2, dot dot xn, depends only on the inherited attributes of A, which is the second part, or the attributes of the symbols x1, x2, dot 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 xj minus 1, which appear to the left of xj in the production. So let us take a look at this with some more details, more attention. So you have the L attributed definitions. L attributed. So this means, of course, it means inherited from parent. So as you can see, that it depends on the inherited attributes from the parent plus attributes from left siblings. This is an interesting extension. So L attributed means it will inherit only from parent, inherit from parent or from its left siblings. So this is important. Now, this is L attributed. So if you have a grammar like this, A producing X, Y, Z, and suppose Y has an attribute Y dot A, it can only depend on A dot S and X dot, say, G or something like that. But the attribute value A cannot depend on Z, then it is not L attributed. Okay. Now, please note that L attributed definition depends only on inherited attributes. Okay. So L attributed definition only puts restrictions on inherited attribute. This is very important. Restrictions only on inherited attributes. Okay. What it means is that there is
So there should not be any synthetic attribute, I think.
no, that is not the point. There is no restriction on synthesized attributes. Okay. So in L attributed definition, there is restrictions only imposed on inherited attributes, but there is no restriction on synthesized attributes. So they can occur freely. So that means if you have a grammar which consists only of synthesized attributes, it is L attributed as well. Okay. So please note these. So if your grammar only has synthesized attributes, that is to say, it is S attributed, because by definition, S attributed grammars can have only synthesized attribute, then it is L attributed as well. This is a fundamental mistake a lot of people make. They think that if a grammar consists of synthesized attributes, then it cannot be L attributed. It is not at all true. Any synthesized attributes is L attributed as well. But not all inherited attributes are L attributed. Please note this. So
But sir, I had a question here.
Yeah.
Sir, if an attribute is synthesized, then it is violating the property of inheritance.
True.
So, sir, if it is not inheriting, so how can I say that L attribute it is?
No, that's what I'm saying. The restriction says only about inherited attributes. So you can have inherited attribute and synthesized attributes. We are not imposing any restriction on inherited on synthesized attributes. If you have inherited attributes, this is the restriction. So that means your synthesized attributes don't even count in case of L attributed. They can just occur. That's it. But if you have an L attributed grammar, that means it cannot depend on right siblings. The inherited attributes cannot depend on right siblings. Synthesized attributes are not at all considered. Means they can occur. They will be just be like this. Okay. So please note this. So you might see this statement that every S attributed definition is L attributed as well. Why? So in that case, you will say that restrictions of L attributedness given by 1 and 2 apply only to inherited attributes. So every attributed definition which consists only of synthesized attributes will always be L attributed, because there is no restriction on synthesized attributes anyway. That's it. This is also very important. Here is an example of a non-L attributed syntax directed definition. You can please study it later on. Okay, now here I have shown one example, which is a parse tree for 9 minus 5 plus 2, and the corresponding grammar is this guy. Okay, so you can, okay, I think I'll probably switch here. So this is the grammar. E produces T or R, T produces num, and the corresponding action is print num.val. R produces an operator, add operator, then T and R1. So it's a recursive definition, right recursive definition, or epsilon. And you can see that immediately after T, the print action is embedded before R, the second R occurs, which is R1. So adopt.lexim is basically plus. So can you tell me what kind of grammar is this? I mean, what kind of action it is doing? Okay, let us take an example.
Sir, in the second line, it is, sir, inheriting, sir.
It is the
T.
second line.
Sir, R is inheriting T.
No, R is not inheriting T. It is val. Val is important. Okay. So this is actually, I'll show you what it is doing. Okay, just a second. Just wait. So E producing TR, R producing plus TR, and epsilon, or T producing num. Okay. Now I am trying to do 9 minus 5 plus 2. So this is the string I need to parse. 9 minus 5 plus 2. Let's see what is happening. Okay. So let us look into the grammar like this. So E producing T and R. Okay. And R producing, say, minus T and R, and then this guy is producing plus T and R. This is epsilon, and this one is 9, this one is 5, and this one is 2, I think. I think this is the parse tree. Yeah. Okay. So here, as you can see, T producing num. So here, the action is print num dot value. So this is produced first. So it will print num dot value. What is num dot value? That is nothing but 9. So it will produce 9 first. Then
Sir, এটা কি আপনি bottom up approach করছেন?
Doesn't matter. That's what I'm saying. Just look at it. Okay, it doesn't really matter. Okay, now R producing minus T and R. So after T is evaluated, after this guy is evaluated, then only it will come to this guy. And in between, that print statement of add op lexim will be there. So that means what? T will be printed first. So 5 is printed, and then it goes to this branch. So this produces 5, this printed print, this print happens here, and then it goes to this branch R, and in between here it is actually producing the print adopt lot lexim, which is basically here minus symbol. Okay, and then it goes to this guy, and here again plus, then it is producing 2, and then after printing 2, it goes to R, which is producing epsilon. But before going there, this is the second operator printing statement, which is plus. So this is basically your postfix expression corresponding to 9 minus 5 plus 2 as per the rule. Now you can ask this question, sir, is it happening in a bottom up manner or is it happening in a top down manner? Doesn't really matter, because as you can see, if you have produced E producing TR, since there is no inherited attribute involved anyway, so it doesn't really matter whether it is top down or bottom up, because you are essentially making the action after the branch is evaluated. So once num is evaluated, then only you are printing the value. So you are printing 9. So it doesn't really matter whether you are doing it in a top down manner or bottom up manner. So you keep on printing the digits, but the only thing is that in between printing the digits and going to the other branch, you are printing the operator. Okay. So suppose it is a bottom up parser. So what will happen? 9 will be producing T, then T will be producing 5, and yeah, I mean, if you are doing a bottom up manner, then what will happen is you are going to reduce plus TR first. Okay, so that means plus should have been printed first, then minus. So it's not happening. So yeah, it is basically a top down evaluation we are talking about. Okay, I'm sorry, Pranay. So you will get this kind of output 9 5 minus 2 plus if you are using a bottom up evaluation of this parse tree. Top down evaluation of this parse tree. Am I clear?
Yes, sir.
Yeah, if it is a bottom up one, then what will you get? You will get 9, then you will get 5. Okay, then you will get 2, then you will get, so you will get 9, 5, 2.
Minus plus, I think.
Yeah, then you will get plus.
Sorry, plus minus.
Then you will get minus. Okay. So let me see what they are doing here. So here what they are doing is, they haven't mentioned actually. So yeah, it depends on how you are traversing the tree. So if you are traversing the tree in a top-down manner, it will be 9, followed by 5, followed by minus, followed by 2, followed by plus. If it is in a bottom-up manner, it will be 9, 5, then then 2, then 2, then plus, then minus. Yeah, that is how it would be done. Okay, good question, very good question. It is not mentioned how they are doing it. Okay, now we come to the restrictions which make things complicated. What is that? When designing a translation scheme, we must observe some restrictions to ensure that an attribute is available when an action refers to it. This is very important. Like for example, if you go back to the earlier diagram of that minus 101, here you can see this is a complex situation because your num value depends on the neg sign. So if it is available, then only num can evaluate properly. Okay. So in that case, the neg attribute is actually better if you are using a bottom-up parsing. Whereas if you see the pause attribute is coming from list to bit, list to list, or list to bit. So it is inherited attribute. That means if it is in a top-down manner, it is better. Or if you are doing it in a bottom-up manner, you have to be careful how to do it. Okay. So that means, like for example, when bit is evaluated, if pause attribute is not available, then bit.val cannot be computed. Please note this particular grammar. Here you see that bit.val depends on bit.pause, but bit.pause is only available from list. But list.val again depends on bit.val. So that means when bit.val is calculated, bit.pose should be available. When list.val is calculated, bit.val should be available. Got my point? Okay, so this is a very fundamental restriction and it's an obvious one also. So that means when designing a translation scheme, we must observe that the attribute value is available when an action refers to it. These restrictions motivated by L attributed definition, because in case of S attributed, it's not a problem. You just embed the action at the end, and if you do a bottom-up parsing, it's no problem. If it is a top-down parsing, yes, you will get some output. It might be different than what you are expecting. So only problem happens with L attributed definition, where you have a mixture of inherited and synthesized or just inherited ones. So in that case, you have to make sure that an action does not refer to an attribute that has not yet been computed. This is the most important point. So in case of synthesized attributes, it is easy to do. In case of inherited, it is not so easy to do. So for S attributed definitions, it is the easiest case because we can construct the translation scheme by consisting of an assignment for each semantic rule and placing this action at the end of the right side of the associated production. So what will happen is, you make sure that when T is available, T1 and F, their attributes are available as well. So that you can do only when you embed the action at the end, so that you know that T1, like for example in this case, T producing T1 star F. So if T dot val depends on T1 dot val and F dot val, you have to just make sure that T1 dot val and F dot val are available. How can you make sure that one? You know that at the end, if you put the action at the end, that means T1 is also already evaluated, F is also already evaluated. So both of their values are available, attribute values are available, and hence you can compute T easily. So for an S attributed definition, you just need to embed the action at the end of a production rule. For a general case, it's not so easy. Okay, I'll start with that and I'll try to complete it by tomorrow. Okay, so in the second case, when we have both inherited and synthesized attributes, we should be careful. Okay, what are the careful things we need to be bothered about? First, inherited attributes for a symbol on the right side of a production must be computed in an action before that symbol. Do you understand this point? Let me explain. I'm just going to explain it. So an inherited attribute for a symbol on the right side of a production must be computed in an action before that symbol. So that means if you have something like this, A producing B, C, and D, and you are trying to compute C dot in. So C dot in may depend on F of A dot in and B dot in. So that means both A dot in and B dot in should have been computed before we try to compute C dot in. That is the most important point, which is not always possible. So an inherited attribute for a symbol on the right side of a production must be computed in an action before that symbol. Okay, that is the most important point. Second is, an action must not refer to a synthesized attribute of a symbol to the right of that action. Okay, so action must not refer to a synthesized attribute of a symbol to the right of the action. So that means like this. So for example, you have D at the end, and you are saying that C dot S is F of D dot S. This is not possible. Why? Because when you are computing C dot S, you are using D dot S. But you know that D dot S is available only when this guy is fully evaluated. Am I clear? So this is not possible because by the time you are computing C dot S, which depends on D dot S, D dot is not D dot S is not yet available. So a clever action could be to place this at the end, which is okay. But that is also not always possible, as we will see. So you can say this, that C dot S is f of ds, because now your D dot S is available. This is available. So this is very important. An action must not refer to a synthesized attribute of a symbol to the right of that action. Third, a synthesized attribute for a non-terminal on the left can only be computed after all attributes it references have been computed. The action computing such attributes can usually be placed at the right-hand side of the production. Okay, so very important. So if you are trying to compute the synthesized attribute of a non-terminal on the left-hand side, say in this case, say a dot s, then definitely it will depend on b dot s, c dot s, and d dot s. So you should make sure that all of them are available. Like in case of a top-down parser, that is not true, because when you are computing a dot s, b dot s, c dot s, and d dot s may not be available. So how you handle these? So these are some important restrictions for general cases, and as you will see, these are not so easy to handle. We have to take lots of roundabout measures. We have to use things like marker non-terminals. You have to use things like backpatching, which are very interesting techniques. We will keep on learning as we go forward. Okay. Now, let us look into this example. A is producing A1, A2. Okay. And A1, A produce A. So let us take this example and see why it is a problem. Okay. So you can see you are computing A1 dot in and A2 dot in after A1, A2 are evaluated. And basically A1, A2 are nothing but A, and you are printing A dot in after evaluating A producing A. So let us see this expression. So I need to parse AA, double A. So what is double A? How is it created? Very easy. So S producing A, and this guy produces A, this guy produces A. This is the parse tree. Very simple. Okay. Now, look at this. Here what it is doing is, it is trying to print A dot in. But A dot in is what here? Here also A dot in. What is A dot in here? We don't know. Because as you can see, A dot in will be available here. A dot in equal to 2, and this A dot in equal to 1. So this A dot in and this A dot in are available only after you have done evaluating both these A's. But both these A's in turn are creating small A's, and they are trying to print A dot in, which are not available. Because as you can see, first this will be done, then second this will be done, and third this action will be done. So you are trying one before you have done 3. So 1 depends on 3, and you are trying 1 before 3 is done. So that means it's not going to work. So you should be careful. we find that the inherited attribute a dot in the second production is not defined. That means here it is not defined when an attempt is made to print its value during a depth first traversal for the parse tree of the input string AA. Okay, we have just explained this. So these kind of problems can come, and it will be very difficult to debug these kind of problems unless you know what are the restrictions and when to put the actions, where to put the actions, and how to print it. Okay, so I give it as a home assignment to you to find out where to put the values of inherited attribute of A so that it can print A dot in by the time it is trying to evaluate A producing capital A producing small a. I leave it as an exercise for you. Okay, so correct this. So correct this. Write rules to correct this. This is your home assignment. Okay, I want to see if anybody has done it. Just give it a thought. Just the action A dot in has to be produced somewhere, has to be placed somewhere else, has to be embedded somewhere else, and show for AA how it is correctly going to do that. That's about it for you today. We'll be coming back tomorrow to complete this and go to the intermediate code generation as well. Okay. Thanks, everybody. I don't have any time for questions. I'll send you this PPT and you keep thinking about it, and tomorrow we'll be discussing all these things.
Thank you, sir.
Welcome. Welcome. I have taken the attendance, so don't worry. You can leave now if you want.